Hi students, in this video we will discuss uh, about circular motion and kinematics of circular motion and relative velocity concept. Okay. Circular motion basically we can categorize into two types, uniform and the other one is non-uniform circular motion. Okay. So what's the main difference between uniform and non-uniform circular motion? If a body is in uniform circular motion, then in such a case, the angular velocity is constant. Okay. But whereas in the case of a non-uniform circular motion, angular velocity is varying. Okay. So we can also understand that we can also differentiate uniform and non-uniform circular motion by considering the speed of that particular particle going in a circular path. So if a body is going in a circular path, it is said to be uniform. Okay. If at any point of time as it goes in a circular path, the speed is same throughout its motion. Okay. So as the body goes in a circular path, I am assuming that it goes in anti-clockwise direction in this case. So definitely at different positions on the path, the tangents drawn will be different. So the direction of velocity will be definitely varying. But if the speed remains constant, though the direction of the velocity is varying, then that circular motion is said to be uniform circular motion. Okay. So in non-uniform circular motion, what basically happens as the particle goes in circular path, so at different points in the path, the velocity direction definitely changes. Direction of velocity changes both if it's uniform or non-uniform, but the primary difference between these two comes when we talk about the magnitude of velocity. In non-uniform circular motion, at different point in its path, the magnitude of velocity is going to be different. Okay, suppose here if it's v1, here it is v2. Okay, so that's the basic difference between uniform and non-uniform circular motion. So whether you take the uniform circular motion or non-uniform circular motion, basically the velocity is changing. We know that velocity is a vector quantity. That means it basically has both magnitude and as well as direction. So whenever you have a vector quantity, if either the magnitude changes or the direction changes or both things related to the vector changes, then in that case, okay, the vector quantity is said to be changing. In uniform circular motion, the velocity is said to be changing because though the magnitude of velocity does not change, the direction continuously changes, hence it is said to be changing. In non-uniform circular motion, what happens is, so here both direction and as well as the magnitude of velocity are changing, hence the velocity is said to be changing, hence it's called as non-uniform circular motion. So whenever there is a change in velocity of a body, then such a body is said to be undergoing acceleration. So we have defined acceleration as the rate of change of velocity. If we use that particular aspect or the particular definition of acceleration and proceed with it, so we will get acceleration for a body going in a circular path. Suppose if we are dealing with uniform circular motion, if a body is going in a uniform circular motion with a constant speed, let's say the radius of its particular path is given by r. Okay, if it's going with a constant speed v, then at any point of time the speed would be the same, and mathematically we can prove that the acceleration of this particular particle when it goes in circular path, at every point in its path the magnitude of acceleration would be same and the direction of acceleration would basically be towards center, hence we also call it as centripetal acceleration. As the particle goes in circular path, okay, At every point the direction of velocity is along the tangent, whereas the direction of acceleration is along the radial direction, which is directed towards center. See that in this case, okay, so can we say the velocity is changing? Yes, velocity is variable, hence we have acceleration. Then what about acceleration? Is the acceleration of the body in this particle changing? So if you look at its magnitude, the magnitude doesn't basically change, because magnitude depends on speed of the particle and radius of the path followed by it. Since v doesn't change, AC also does not change. But if you look at the direction of the acceleration, so as we just discussed, the acceleration at any point in its path would be directed towards the center. So the direction is continuously changing as it goes in the circular path. Hence I can say AC is varying, it's variable. Okay, it's not remaining constant. Hence we can't say that the acceleration is constant just by looking at its magnitude, because direction also matters because it is a vector quantity. This is related to the centripetal acceleration. Acceleration of a body undergoing uniform circular motion, or we can also write it as, V can be written as R into omega, where omega represents the angular speed of that particular particle, which is equal to R omega square. So if a body undergoes uniform circular motion at any point, its acceleration magnitude is going to be the same at any point in its path, which is going to be v square by r, or r omega square, and it will be directed towards center. Now let's discuss briefly regarding non-uniform circular motion. Okay. One more small point I forgot to tell you here. So the time taken in this case would be time taken to complete one circular path. Okay. Since it moves with a constant speed, if it completes one circular path, it needs to cover a distance of 2 pi r, which is nothing but the perimeter of that particular circle. So time taken to complete one circular path would be the perimeter of the circle divided by the speed with which it was going in the circular path. Okay. Or we can also write it as 2 pi by omega, so where omega represents the speed of the particle, since v is equal to r into omega. Okay. Now let us try to write relations related to the non-uniform circular motion. Okay. Let's discuss briefly about it. So here in the non-uniform circular motion, the particle basically goes in circular path. It's both magnitude and direction of velocity are changing in this case. Magnitude and direction of velocity v basically changes. Okay, so if let's say at some particular instant of time, let's say when it was at this point, let's say A, center is represented with O, the radius of that particular circular path is r. So here the acceleration of that particular particle, we can resolve it into two components. One is the radial component, which would basically be perpendicular to the tangent or perpendicular to the velocity, and the other is tangential component, which kind of will be parallel to the direction of velocity. So if we look at the radial component, we also can call it as a centripetal component of acceleration. So the other component is tangential component. This tangential component, if it's in the direction of the velocity, then in that case the magnitude of velocity would basically increase with time. Suppose if AT is parallel to v, then what would happen to v? V would keep on increasing in magnitude, increases. If AT, the tangential component of it is anti-parallel to v, then in such a case, so what would happen to v? So v would keep on decreasing. It is parallel to v and AT anti-parallel to v. So how do we find the magnitude of both of them? So the centripetal component of acceleration at that particular instant is given by v square by r. So if at this instant we wish to find the centripetal component or radial component of its acceleration, which is equal to square of speed of the particle at this instant divided by the radius of its path. So since v changes in this particular case, okay, the magnitude of velocity changes, so the magnitude of centripetal acceleration will also keep changing. Okay. And next thing here, if you how do you find AT? So AT, we can write it as d by dt of v. So here v does not represent the velocity, it represents speed, or it just represents the magnitude of velocity, because here the radial component, which is perpendicular to the velocity, is basically responsible for the changing the direction of its velocity, but whereas the tangential component of acceleration is responsible for changing the magnitude of velocity. So it would basically have both centripetal component as well as tangential component, and the resultant of these two would be the actual acceleration of that particle going in that particular circular path. Okay, so this is about the circular motion briefly. So we will discuss a few problems in the later video. Okay, let's discuss briefly a little bit about relative motion or relative velocity. Relative motion. So to get a better understanding of the relative motion, okay, so let me use a little bit of vectors and what we have discussed regarding position vector, displacement and triangular vectors, all those things earlier. So imagine we had two objects, two bodies moving in xy plane. I'm considering xy plane. The same explanation can be used even if the body was moving in 3D space. Let's say this was xy plane. Let's say we had two particles. One of the particle represented as A. Let's say at this instant of time it was at x1 comma y1. Okay, and the another particle B at this instant was at x2 comma y2. Now the position of this particular particle at A, let me represent it as r1 bar. R1 bar represents position vector of A, whereas the position vector of B is given by R2 bar. So R1 bar is given by x1 I cap plus y1 j cap, whereas R2 bar is given by x2 I cap plus y2 j cap. So the both bodies A and B might be moving, so the positions of both of them will definitely change if they are moving. So if A is moving, its coordinates will not be x1 comma y1 all the time. Similarly, the coordinates of B would also be moving as it, if it's moving. Okay, coordinates tend to change. Now here the positions of both the particles A and B are represented with respect to the reference point, where the reference point is considered to be the origin. Now look at what I'm going to represent. So this is a vector directed from A to B, okay, or we can call it as position vector of B relative to A. So what does this vector basically mean? So what this vector RBA basically tells us is what's the position of B, okay, when seen from the position of A. So if you can evaluate RBA, so it tells us what's the distance of B from A and in what direction. So B seems to be present as seen from the position of A. So if you make use of triangle of vectors, okay, you see R1 bar and RBA bar, they're kind of drawn in order, but whereas R2 bar is drawn in the reverse order to close a triangle. Okay, so if we use the triangle of vectors, so we would basically get R1 bar plus RBA bar is equal to, I think it's kind of confusing. Let's write instead of RB as R21. Just a minute. That would be easy, guys. Position vector of second relative to the position of 1. Or we can write R21 is equal to R2 minus r1. r2 bar is the position vector of the second body with respect to the fixed reference point which I've taken to be the origin. r1 bar is the position vector of the first particle with respect to that reference point O. r21 is the position of B relative to the position of A. Now if you differentiate this with respect to the time, so d by dt of r21 is equal to d by dt of r2 bar minus r1 bar. So we would basically get d by dt of r21 bar gives us velocity of second body as seen from the position of first body or as seen by first body. Then we would get d by dt of r2 bar, which is v2. So v2 bar would be the velocity of the second body with respect to that fixed frame, okay, which is the with respect to O minus v. So this is velocity of 2 relative to 1. Similarly, we can also write velocity of 1 as seen by the person 2 or relative to is equal to velocity of the first person minus velocity of second person. Okay. Similarly, if we differentiate this velocity with respect to time once again, d by dt of v21 bar is equal to d by dt of v2 bar, okay, minus v1 bar. So d by dt of v21 bar would be a21 bar is equal to a2 bar minus a1 bar. So acceleration of second particle related to the first particle would be acceleration of second particle minus acceleration of first particle. So this is the basic what do we say, understanding of the basic terms in relative velocity concept. Now let's use these concepts in order to discuss a few specific cases from where problems can be framed. Okay. First, let's say we had a question something like this. Let's say we had two trains. Okay. So what do we have? Train A, train B. Okay. Let's discuss two scenarios where in the first case, let's say the A was moving with V1, B was moving with V2. So let's say the lengths are given by L1, L2. Now our intention is to find, so velocities of both the trains are given, assuming that they are moving in the same direction, and their lengths are also given. Now our intention is to find with what velocity do they move, I mean after what time does basically trains cross each other, assuming in this case V1 is greater than V2. So they are kind of moving in two tracks which are parallel to each other, and the one which is behind moving with a speed greater than the one which is moving in the front. So basically the one behind would definitely cross the one in the front. Okay. Now the question is after what time it would be able to cross. So time in the sense, okay, it's at this moment the front of train A is just adjacent to the back portion of the train B. Okay, so if it completely crosses, this is how the situation is going to be. At the moment when A completely crosses, this is how it's going to be. Okay, so at the moment when A completely crosses B, so the back of train A would just be at the position of the front of train B. So now, so what would be the time taken to go from a kind of this kind of arrangement to this kind of arrangement? Now initially at this moment, okay, we can solve this problem without using relative motion concept, but we will try to solve it using the concept of relative motion. Okay, so let me imagine it something like this. Let's say there were two people, okay, one you assume in train A and the other assume in train B, so both of them looking at each other. So my intention is I will sort of assume the positions of the two people such that it's easy, okay, in terms of calculations. I will assume, wherever you assume the two people in both trains, it doesn't make much of a difference. You can still calculate the time taken. But if you assume it in such a way, such that your calculations become easier, it's better. Now I have assumed a person, one in the back of the train A, one in the front of the train B. Let's say, so this is, let's call him the first person, let's call him the second person. Now let's say the first person is continuously looking at the second person. Okay, so now at this moment, the first person, when he's looking at second person is at a distance of, how far is the second person as seen by the first person? So it would basically be, okay, L1 plus L2. So if the trains completely cross each other, then they are side by side. So there is no separation between them. So if the trains cross each other, the displacement of the first one, okay, focus on the points very well. The displacement of the first one as seen by the second one. If second one is continuously looking at the first one sort of seems to be moving towards him because the separation between them keeps decreasing. So, and finally it becomes 0. So the displacement of the first one as seen by the second one is L1 plus L2. Okay? Because he has to go from sort of this separation from second person to a separation of 0. So if you are the second person looking at the first person, it looks like the first person is approaching you, and he travels a displacement of L1 plus L2, okay, before he reaches you. Then what about the velocity of the first person as perceived by the second person? So we can write it as v1 minus v2. Remember that it's in vector form. Velocity of the first person is in the right direction, hence I will consider it to be negative, okay, minus, well, second person has a velocity in the right direction, hence I will consider that also to be negative, so v1 minus v2. So the first person basically has to undergo this much relative displacement with this relative velocity during the time the train A completely crosses train B. Now since there is no relative acceleration, time taken would be the relative displacement divided by the relative velocity, which would be equal to L1 plus L2 divided by V1 minus V2. This is the time after which A would completely cross B. Now let's take another case where the two trains were traveling in the opposite directions. So let's assume something like this. Train A, 1 minute. Train A, train B. Say A is moving in the right direction, B is moving in the left direction. Let's say A has a length L1, B has a length L2. Now also the same question. We intend to find the time taken by both the trains to cross each other. Okay. So now I would imagine the two people again present at the ends of the trains. So now if the two trains completely cross each other, okay, just a minute. Now if both the trains completely cross each other, then this is what the situation is going to be. Just 1 minute. B would be something like this, and A, the back of the train A has just crossed train B. Okay, this is L2, this is L1. So this is where the two persons are now. So originally they were separated by a distance of L1 plus L2. Now when the trains completely cross each other, they are separated by a distance of 0. Imagine you were this person looking at this person. Initially, so this first person is at a distance of L1 plus L2 from the second person. But as the second person keeps looking at the first person, so the first person kind of seems to be traveling towards him. So when in the interval when both trains cross each other, the displacement of the first one as seen by the second one would be L1 plus L2. Then what about the velocity of the first one relative to second one? So V1 bar minus V2 bar. So in this case, the velocities are in opposite directions. The first one has a velocity in the right direction, hence we will consider it to be positive, whereas the second person has a velocity in the opposite direction, hence we will consider it to be negative. So the relative velocity is basically v1 plus v2. Now the time taken for the two trains to completely cross each other would be the relative displacement. It's something like displacement by velocity. So anyways, the two trains do not have any acceleration, so the relative acceleration would be 0. So we can directly write time is equal to displacement by velocity when they do not have any acceleration. So we can write L1 plus L2 divided by V1 plus V2. So that would be the time after which they would basically cross each other. Okay, and then this is a little example related to the relative velocity in one dimension. Let's discuss a few cases in two dimensions. So if we go to two dimensions, okay, so we will discuss two specific scenarios. One is the situation related to the riverboat problems, and the other one related to the rain man problems. Okay, so first let's focus on riverboat problem. So imagine, okay, we have a river. So we have a river whose width is basically, let's say, d. Okay, or what I mean by the width is the distance between the two banks of the river. Let's say VBR. Okay, so represents velocity of boat with respect to river, or in simple terms the way to understand is what the boat would have a velocity if it was driven in still water. Okay, in a lake, let's say you take a boat in a lake and then you drive it or steer it, the velocity with which it would move in that still water or the water which is not moving, that is VBR. But once you have a river, okay, so basically if a boat is driven in a river, apart from the velocity it has due to the engine, apart from that, due to the river flow also, the velocity of the boat would be affected to a certain extent. Okay, so the velocity of the boat that it will actually have when it's driven in river is nothing but VB, and VR represents velocity of the river. So what we mean by the velocity of river is velocity of water flow present in the river. Okay, let's say water is flowing in the right direction. So now in this case we will discuss two specific scenarios. So one is the case where you wish to cross the river in the shortest path. So what's the shortest path basically in this case? So the shortest path that's available to go from one bank to another bank is where you start at a point and you reach another point on the other bank. Okay, so which is right across the point A. Okay, so that's the shortest path where the displacement taken when you go from one bank to the other bank would be the shortest. But if you try, so imagine you take a boat and you try to steer it in that particular direction. Okay, so let's say one second. So VBR can be written as velocity of boat with respect to ground minus velocity of the river, or we can write VBR plus VR is equal to VB. So your VB represents the velocity of the boat as seen by a person standing on the bank of the river. So if you steer your boat, just 1 minute. So let's say we try to steer boat in this particular direction, but what would happen? Okay, velocity of river would be in this particular direction. The boat kind of goes in this direction. So this is the direction in which boat would actually go if you try to swim right across the river. Okay, so that is not a proper way to drive a boat if you wish to cross it in the shortest path. Then what's the best thing to do? So what we do in this particular case, okay, just 2 minutes. So if this was the river, so we drive it in a particular direction, something like this, okay, such that VBR plus VR, okay, as you can see from here, VBR plus VR gives us VB. So VR, VB. So we have to drive at certain angle with the river flow such that, okay, so the VB would come perpendicular to the river flow. So we should drive something like this. Let's say this angle is theta, then tan theta is given by VR by VBR. So we must drive it at an angle, at this angle to the perpendicular of the river flow, okay. Then you will be able to cross it in the shortest path. Now what would be the time taken to cross the river in this particular case? Okay, so time taken, so if it crosses the river along the shortest path, as it goes from A to B, the displacement is basically d, and the component of velocity along that direction is for the boat is VB. So we can write d by VB. So which one we can write it as d1. So if you see from the this right angle triangle that we have here, VB can be written as root of VBR square minus VR square. Okay, so this is the time taken to cross the river, okay, in the shortest path. Now let's discuss the next scenario where we wish to travel a river and we wish to go from one bank to the other bank along, taking the least amount of time. Okay, so I'm not going to give a detailed explanation regarding this. I'll give you simple one that directly, okay, since you already learned. So if you wish to cross the river in the least time, okay, what we must do? So we must drive the boat, or the boat should have velocity with respect to the water perpendicular to the river flow, and velocity of the river flow would be in this particular direction, and as a result velocity of boat would be in this particular direction. So if we need to make it cross the river in the least amount of time, VBR must be perpendicular to VR. And now let's calculate two things in this particular case. So one is something called the drift, okay, and the other is the time taken by to cross the river. So if it basically crosses the river, it would basically be due to this velocity, okay, or time taken to cross could be the displacement. Just 1 minute, let me explain things clearly. It would basically go in this particular path. So if it starts at point A on this particular bank, it would reach the other bank at point B. So this is the actual total displacement. So this, let's call it displacement along y direction. Let's call it this as displacement along x direction. So the displacement along y direction would basically be the width of that river, which is given by d, and the component of velocity the boat would basically have along that direction is VBR. So this is the time taken to cross the river, and this displacement that it has parallel to the river flow, so we can call it as the drift. Drift is basically Sx, so which would be equal to the component of velocity in that direction. You see here, VB is the velocity of the boat as seen by a person on the bank. So if you resolve it into two components, one perpendicular to river flow and another parallel to the river flow, this would be the component perpendicular to the river flow, and this would be the component parallel to the river flow. So the displacement parallel to the river flow would be, so velocity component parallel to the river flow into time taken to cross the river. So which is, this is the drift of that particular boat. I hope you got a basic idea. In the next video, we will discuss a few problems related to all these things. Now let's discuss briefly relating to rain man problem or rain umbrella. Here also quite simple. We make use of the basic, okay, the mathematical relation for relative velocity, and we make use of little bit of triangle of vectors. Okay. So let's say a person, okay, is traveling with a velocity Vp in that particular direction, and it's raining in this direction downwards. Let's say it's raining vertically downwards. Now our intention is that, so the first thing I wish to find, what would be the direction of the rain velocity as seen by that person who is actually running in the right direction. For a person who is actually standing on the ground, definitely the drops seem to be falling downwards, but if you are basically moving, then the drops doesn't seem to be falling downwards, they seem to be falling at certain angle. Okay, so we need to find velocity of the raindrops relative to the person. We can write it as velocity of the rain minus velocity of person, or we can write it as Vr plus minus Vp. Okay, so this is what I intend to find, the velocity of the rain relative to the person. So we can write it as the vector sum of velocity of the rain related to a person who is at rest on the ground, and negative of velocity of person. So if Vp is in the right direction, minus Vp would be in the left direction. Okay, and next thing, rain is basically, velocity of rain is basically in the downward direction. Since I am doing the vector sum of two vectors, I have to draw them in an order, and the vector drawn in the opposite order is nothing but Vrp. So for this person, basically the droplets seem to be falling in this particular direction. Okay, so at what angle with vertical? Okay, so this is theta. At what angle with vertical does the drop seem to be falling? So that is theta. Then from the right angle triangle, as you can clearly see, tan theta is opposite side, which would have a magnitude equal to Vp divided by the adjacent side, which is Vr. So tan theta is equal to Vp divided by Vr. Okay, and then, so if the drops seem to be falling in this direction for that person, so if the person has umbrella and he needs to protect himself and he wants to maximize the use of that umbrella, okay, such that he could save himself from getting wet from water droplets, he can kind of hold his umbrella like this. So this is basically the umbrella. So he must hold his umbrella in the direction opposite to the river flow, or making an angle theta with the vertical, where theta is given by tan inverse of Vp by Vr. Okay, now let's discuss another scenario. Let's discuss another case, okay, on more simple example related to this. Let's say we have another example where the rain, it's actually raining, okay, making an angle theta with vertical. Now the question is something like this. Let's say, what should be the direction and magnitude of velocity? I will write the question here. What should be direction and magnitude of velocity of the person such that it seems to be raining vertically to him. So that means basically they are saying us that the velocity of the rain relative to the person must basically be downward direction. Okay, for that, what should be the direction and magnitude of velocity? So we'll make use of this relation. Velocity of rain relative to the person is equal to velocity of rain plus minus velocity of person. So basically the vector sum of velocity of rain and minus Vp would give us velocity of rain relative to the person. Basically this is theta. Now, so if minus Vp is in this direction, minus Vp should definitely be in this direction. Only then Vr plus minus Vp would give us Vrp. So basically the person has to be running in the right direction in this particular case. And with what magnitude should he be running? We will try to express that in terms of Vr and theta. Okay. If you see there, we can I mean, VR is like the hypotenuse, VP is the opposite side to theta, and so which trigonometric ratio contains opposite side and hypotenuse? So we have sine theta. Sine theta is equal to opposite side would have a magnitude equal to minus VP bar, which is VP divided by hypotenuse. So the person basically should be running with a speed of VR into sine theta and in the right direction. Then in that case, the rain with respect to that person, it seems to be falling, drop seems to be falling vertically downwards. Okay, that's it related to the relative motion. Next video I will try to explain a few problems based on these concepts from motion in a plane, and I will start the discussion of the motion, laws of motion. Okay. Bye bye, that's it for the video.